Let us talk through our second reading here before we go into lab. Today will be pretty quick, sort of like the first mirror lab. So we'll be able to get through that quickly and still make good progress. The terms converging and divergent are often applied to spherical mirrors. Describe which term describes each of the two types of spherical mirrors. So which one converges rays? Concave. The concave makes the rays go together. So that's a converging mirror. When rays hit on a convex mirror, they diverge. They go off in different directions depending on where they hit. And those terms are used interchangeably with concave and convex mirrors. Spherical aberration is a big problem for things that you want to make really good images with. What is spherical aberration? Alex?
Wasn't it when all the rays parallel to the principal axis, they don't meet to a single point?
Right. The trouble is that when we draw these out, we always say any two rays hitting go through the focal point. But that's not actually the case with a spherical mirror. If we have one closer, and I forget exactly which way it's going to be bent, and say it's bent a little more, might bend there. If we have one farther away, it would be bent down like this, so that it makes it more of a fuzzy image. It doesn't technically they don't technically all meet at the focal point, although when we sketch them, we approximate that. In order for this to actually work, we need the shape that does this, which is a parabola, rather than part of a sphere. But what's the problem with parabolic mirrors? I know you know, Candy, because I read all of yours.
You read all of my answers?
Yes. What's the problem with the parabolic mirror?
Oh, parabolic mirror, that's the next question.
Yeah.
They're really expensive. We only use them when we use really clear images.
Yeah. These are pretty easy to grind. If we just have something spherical and grind it away, it will become a spherical mirror. But a parabolic mirror is a different shape, and it's much harder to grind those evenly. Question, Kayla? Yeah, these are usually ground, although, well, they used to be ground. The really, really big mirrors, we saw in a video, I think, last chapter, are kind of spun out so that they get an appropriate shape. Those were, though, parabolic mirrors that were spun for the big, really big telescopes, because even though they're extremely costly, as Candy said, when we need an image clear, and if we need a really clear image badly enough, we'll spend the money. Describe the location of the focal point for both convex and concave mirrors. This one shows pretty well where the focal point is. Let's get rid of those rays. In front of the mirror, on the reflected side, convex is, as we've been saying, behind the mirror. So where the light doesn't actually go. So the questions, 3 rays of light originating from an object often used to graphically determine the location of an image formed by a concave mirror. Describe how this is accomplished. What I was looking for there was, and this one's pretty good, those rules that we went over and how to apply them. Those are the 3 rules that I want you to be comfortable using. This goes for that question, and for P, how are the 3 light rays from an object used to find the image location formed by a convex mirror. Flipping through, like I say, I didn't have a chance to read all of them. Those answers were a little brief, so make sure you can describe how those 3 are each reflected. So what are the conditions coming in, what are the conditions reflected, and then where they meet is where the image is formed. Number N. Does a concave mirror always form a real image? No. Does it ever form a real image? Okay, so when does it form a real image? When does it form a virtual image? We'll get David a chance.
So it forms like a, because it kind of depends on like the angle that the object is, because that moves the focal point.
Okay,
So then if it's more of an angle, the focal point goes closer to the mirror.
correct.
And then, so then if it's not, then I don't know the other part.
Okay, so you've told us where the focal point goes, but not where an image might be formed. Okay,
So if the object is behind the focal point, it creates a real image. If it's in between focal point and the virtual.
if the object is out here past the focal point, then they will converge somewhere out here as well and form a real image. But if the object is inside this focal point, then the image will be virtual, and this is where we saw the magnification we saw before. Does a convex mirror always form a real image? No, it never does, right? There, on a convex mirror, those rays are never going to converge anywhere in real space, so you're never going to get a real image. It's always a virtual image. When using the mirror equation, how can you tell if the image formed is real or virtual? So this is referring to the equation that we used in the homework and discussed a couple days ago. What about that equation helps us? What's negative? Not M. That's not in that formula. The mirror formula F is negative if it's a convex mirror and positive if it's a concave mirror. That alone doesn't tell us. We actually kind of have to assign that instead, but that alone doesn't tell us whether we're going to have a virtual or real image. Object distance, that's always positive. So what does that leave? Image distance. If image distance is less than 0, if it's negative, then it's a virtual image. If it's positive, then it's real. The real side is where the rays really, really meet together. The negative side is the virtual side. Where they don't, we are just tracing them back to where they appear to originate behind the mirror. Okay, and R. This is a toughie, which is why I got the drawings up. An object is placed in front of a spherical mirror, and the magnification is -6. M equals -6. And we saw before that was negative DI over DO. Image distance over object distance, also image height over object height. So those are two ways to describe magnification. And the quotient there is -6. So what can we tell about that? Is the object larger or smaller than, is the image larger or smaller than the object?
It would be larger
How do you know?
because that's the value of 6 is larger than 1.
Yep. So a 6 means that the height of the image must be greater than the height of the object. So it must be a larger image. So it is magnified rather than demagnified. If this were less than 1, the absolute value here less than 1, it would be smaller. Is the image upright or is it inverted relative to the object?
Inverted, because that's what the negative.
Yep.
stands for.
So that's what this means, that it's bigger. That means that it's inverted. So then the last question is it real or is it virtual?
Would it be virtual?
How do you know?
Because since the image distance, like overall, like, cause the default, nothing can be negative at this point. Right?
It cannot.
So then if it, words, if the image distance is less than 0, then the image is virtual. So if the DO cannot be negative, then the DI is negative.
But in order to get this negative, this already has a negative. So the DI must be a positive. So here, let's look at it. First off, this being a bigger image, what does that tell us about the mirror? What kind of mirror must we be using? So when we look at this, at a convex mirror, we're never going to find a magnified image. They'll always be smaller. That object in your mirror is smaller than it appears. That's this kind of mirror. So that must mean that we're using a concave mirror. There are two different ways that we might see magnification from this. One is, we put an object up here. Let's do this. And I'll try and trace these out really quickly. So we've got one line seemingly originating from the focal point, hitting that, and that's reflected backwards, but then we're going to have to trace it out this way. And then we've got another one going parallel to the optical axis that's reflected here, and then we'd have to extend it back. So our image would be right there. And that's certainly not 6 times bigger, but you get the idea. If we found the right spot, it could be. So that's one option. That, of course, would be a virtual image. Does this meet the requirement of the magnification being -6? So if magnification equals negative DI over DO, or also the height of the image over the height of the object, is this going to be -6? Why not? But we already said -6 is bigger.
It's not inverted.
It's not upside down. So in this case, we could not. This DI would be a negative number, so you'd have a negative times a negative number over DO. This can't be a virtual image in this case, because that would make this a positive magnification, which makes sense because it's upright. So this one doesn't work. Let's move this out here somewhere and see. If we move it out there and now trace through some of these other ones. Go like so, through the focal point, and then we go through the focal point, straight. Here is our new image. Could that potentially, depending on my placement of my object, could you conceivably see that as being 6 times bigger than my object? Could it get bigger than it is? Yeah. Could it be, is it inverted? Yes. This is the case where you might see that -6. Is it a real or a virtual image? It's a real image. Because it's out here somewhere in real space. And if I move this closer and closer to my focal point, what I'm going to see is, readjust these, go down here, hit somewhere over there, And this one go down. That one's still okay, bigger and bigger. So the closer this gets to the focal point, the bigger my image gets, and it's always real because it's on the outside of my focal point. But it is also inverted. So this is the case where that would actually happen. In this case, we could only say that it's real. You're only going to get that magnification when it's real. That's a really tough question at your stage of learning to get, and I understand that, but this is the kind of thinking to start looking at. When we were inside the focal point, it was always upright. So that means this the negative part of the -6 can't be fulfilled. Could be 6 times bigger, but it'd always be upright. If we had a convex mirror, it's always going to be smaller. So that doesn't work. And these will actually always be upright as well. So you'll never get a negative and you'll never get something bigger than 1. So the only case that it could work is actually in between R and F. You're going to get magnification and inversion. Very tricky, very specific for that last one.